y'all's rules for that y'all didn't bring them right. I'll have to bring them back to y'all, but it's very important to understand the rules that the book don't quite do a really good job on, right? So I'll have to run some of these off. I'll need to find out how many of y'all have got these. But this is the rules for relay logic. And a lot of the rules that we use for relay logic basically carry over to PLC logic, right? Diagrams. So first rule says what? Control devices such as switches, push button, relay contact, sensor contact, relay and sensor contacts are placed between what? Between L1 and the load. No control devices connect to L2. So all your control devices are between L1 and the load, right? You understand that? Okay. Rule number 2, output devices such as relay coils, lights, small motors, and solenoids must be placed between the control devices and L2. One and only one output can be placed on each rung line. So this guy kind of gets a rung and a line confused with each other, right? You understand the difference? A rung is an electrical circuit that runs between L1 and L2 that consists of one or more lines. Magnetic motor starter overload contacts are the only thing allowed between the motor starter coil and L2. All other rung loads must be connected directly to L2. You understand that? Everybody okay there? You know what an overload is, right? What do we use overloads for? Well, it protects the motor. Motors, what they do is they pull between 6 to 8 times more current when you start them than they do when you run. So we got to start motors, so your overcurrent protection devices are allowed to are sized to let the start current get through, right? You understand? Well, what if the motor stalls? Well, it's not going to pull any more. It's not going to pull any more current than's required to start it, right? But it's going to be pulling starting current all the time. And what will happen to the motor? It'll burn up. It'll burn the motor up, and the fuse won't even burp because fuses are rated at least 150% over whatever you're trying to get through them, right? You understand that? So what we do is we have these devices called overloads that senses overcurrent over time. They don't trip easily. They trip if the motor don't start right. So it won't trip it. It gives it enough time to start, but if it ever stalls or don't start, then what will it do? It'll kick out the circuit. So we have overload sensors, which I didn't put right here, by the way. I'm sorry when I drew this. We have overload sensors that are in series with the motor. I drew my circuit wrong. So these are overload sensors right there. And then these overload sensors control a contact. And that contact goes between a motor starter and L2. So right off the bat, when you're looking at an electrical diagram and you see that contact on, it's normally closed, right? You understand? Because it allows it to work until we get it open. Until we get an overload. And when we do get an overload, it opens the starter. So the starter would drop out, and then the motor would stop, right? You understand that? So that's the only thing that's allowed on the L1, on the L2 side. That's the only control device on the L2 side is an overload. So we call these motor starters. So we got 3 categories of relays. We have control relays. What are these? Well, they're all relays use magnetic coils. You're right, but you're not right, right? That makes sense. A control relay, the contacts of a control relay never leave the control circuit. Never leave the control circuit. So what we usually end up with is we end up with two diagrams. We end up with a control circuit, and then we end up with a power circuit. Right? You understand? But notice the control relay, here's one of its contacts, here's one of its contacts. Right? You understand? The motor don't show contacts because it's part of the power circuit, right? So here's these M contactors down here in this power circuit. You understand that? So a contactor is a power relay, so it's going to be big, right? You understand that? But it don't have overloads. So this would run loads that don't. This would run high-powered loads that don't require overloads, right? You understand? A motor starter has power contacts in it, but these guys are designed to run what? Motors that don't have internal overloads. A lot of motors have internal overloads on them. If those are internal overloads, then you don't have to use a motor starter, you can use a contactor. Does that make sense? So this is the symbol of overloads. It's that normally open contact between the what? The coil on the motor starter and L2. Are we okay? So that's the only thing that's loud between the load and L2, and that's on motor starters. Rule 3, control devices can be connected in what? Series, parallel, series. The connection of control devices does not determine if it's a series circuit, parallel circuit, or series parallel. That's how your loads are connected. And what don't we have in motor controls or PLC? We don't have series parallel, right? We're going to use. We don't have series. I mean, we got a basic circuit. You understand a basic circuit what's the requirements of a basic circuit? Got to have a power source, right? Got to have conductors and got to have a load. And that's a basic circuit. So either we're going to put basic circuits which have one load, or we're going to use parallel circuits, right? So we don't have true series circuits and we don't have true series parallel circuits. Rule 4, multiple rung output devices cannot be connected in series. However, multiple output devices can be connected in parallel, which means they're going to be in a what? Different line within the rung. Everybody understand that? Only one output device can be connected in a rung line. The rule is one or more output on a rung, but only one output per line. There are no series parallel circuits allowed in relays logic. And this is also true in PLC logic, right? Everybody okay? Yeah, so here's a rung. Here's a circuit that's running between L1 and L2. That's a rung. And I've got two loads in this rung, but they're connected in what? Parallel. Yeah. But what is, and this is the way we do it, is that each horizontal line, we call it a line. So this rung consists of two lines. So we can have multiple loads in a different line, right? You understand that? We cannot have, in different lines, but we can't have multiple loads in the same line. Okay, so this would be a two-line rung right here. And then what we do is we come over here and number the lines. So in relay logic, we deal with line numbers. We don't deal with rung numbers. We don't number the rungs. We number the lines. So notice this rung has two lines, and over here we got 1, 2, right? So this is a horizontal, so it gets a what? Gets a number. 3, 4. Well, where's the line? Well, that line is way over here, right? You understand? And anything that lines up, so if I had something bypassing this contact down here, it would still be line number 4. So anything that lines up is in the same line number, right? Does that make sense? Okay. Line 5 is this guy right here. This is line right here. There's only one line in that rung. Okay, so these are lines. So this is a line. So there's 1, 2 lines in this run. Okay. No, these are manufacturer numbers. So what we do is that when we buy stuff, how do we know how to hook them up? Well, what they do is they provide manufacturer numbers. So what I did, so I knew how to hook this thing up, is I wrote down, and I can't see the devices. All I see is the manufacturer numbers. So I know this light bulb right here belongs to what? 1 and 2. So that means I would wire up on that light bulb on numbers 1 and 2. Okay. So these numbers inside the diagram, these are manufactured numbers. Those are not line numbers. Line numbers go on the left of that one. No, I see 1, 2, 3, 4, 5 lines. Those are contact cross-net reference numbers. Okay, so I'll yeah. I understand. So you was talking about cross-reference number. Yeah. Not on top of it. It should be what? Should be underlined. Yeah. So we ain't got that far yet. So that's why you got me confused. So you are exactly right. But we ain't got there yet, right? So these numbers inside here, what are these numbers right here? We call them manufacturer numbers. And what does that allow me to do? So when I draw it, what I do is I get my components, and then I look at the manufacturer. Now, we've got a drawing that actually shows, I'll show you all the book, that shows you what these numbers go to. We got a reference book that we can look. This is assigned by ECI, the people that make that. But all your devices, when you buy them, they literally have numbers on them. They have numbers. So this is a manual motor starter right here. So can y'all see them? 1, 3, 5, 2, 4, 6. Those are put on there by manufacturers. Now what we do when we wire it up, we take these numbers and we literally put the numbers on our drawing. So when we're wiring it, we don't have to keep trying to look at these devices, right? And we know that this push button right here. So I know I don't have the push button up here, but I know this push button right here. This normally closed. The numbers are what? 1 and 2. And then the normally open is what? 3 and 4. And this contact down here on my control relay is what? 1 and 3. Now I notice this has got a 6 and that's got a 6. Well, those are connected inside the relay. It's a single pole. It's a single pole double throw. So I've got a normally open and a normally closed, but 6 is common to both of them. Y'all understand what I mean? Yeah, well, it's a single pole, so that means it's got one switch, but it controls 2 circuits. So this is 6 right here. This would be a normally closed, so I would go from, this would be labeled 6 and 5. This would be a normally open. This would be labeled 6 and 7. But no, both of them are what? Common 6. Well, when I draw my diagram, I'm not going to draw them like this. I'm going to draw them like this. So this is the normally open, which represents what? That guy between what? 6 and 7. This guy is the normally closed, which is between what? 6 and 5. Well, in my motor control diagram, I don't use single pole, single throw switches. I put contacts in different lines, right? You understand, because they're controlling different things. But notice this has got a what? 6, and this has got a 6. Because that's this guy right here, right? So I didn't have to run this wire. I mean, because it was already ran for me. But when I draw it, I have to draw it like that. That makes sense? And Mr. Brown, what do you say these were? Yeah, these are numerical cross-reference numbers. And what do they tell us? They tell us which line this relay's contacts are in. So right there it says this relay has a normally open contact in line 2. I come over here to line 2, and I come across it, and there it is, right? You understand? And then it says it's got another normally open contact in line 3. Here's line 3, and there it is, right? You understand? and then it says it's got to normally close. So normally close, what we're supposed to do is we put an underline under it, which tells us now we're looking for a normally closed contact, and it says it's in line 5, and there it is. And this is the one that I left out because I added it when I originally drew my. Yeah, it's autofocus, and sometimes it don't want to work. Sometimes I can raise it up. Yeah, autofocus cameras because you don't know what they're focusing on, right? Might be. I'll leave this thing in the floor. But it was focused when we started. So most of your control diagrams have 2 circuits. We have what we call the power circuit, right? This is what this is what it's controlling, and then we have the control circuit. The control circuit is usually lower voltage. What advantage does the low voltage have? What advantage does high voltage have over low voltage? More stuff. Good guessing. But the problem we have is what am I trying to get to a device? Am I trying to get voltage? Am I trying to get current? Or am I trying to get power? Powers work, guys. Powers work. So I'm trying to get power to a device. Now, different loads are designed to run. These loads are designed to run around a certain voltage. So the magic thing is the way we calculate power in electronics is power is equal to V times I. That's the power formula. That's our main power formula. Well, we can rearrange this and say I is equal to P over V, just by rearranging that formula. Now, I'm trying to get a certain amount of power, so we'll leave that constant. So let's say I'm trying to get 100 watts of power, and I'm trying to get it at 5 volts. Then that's going to require 20 amps. Let's say I'm going to get 100 watts of power at 100 volts, then that's going to require 1 amp to get that power. Now, the problem we have is there is no such thing that has no opposition at all. Everything that we know has resistance opposition. So anytime I put current through an opposition, it drops a voltage. It's just like your blood. So that's, if you got opposition in your blood vessel, then what happens? It causes the pressure on the inlet side to be higher than normal, and the other one lower. That's not happening in here. The voltage, what would happen? The amount of voltage drop we get is equal to the amount of current flowing through there and the amount of resistance everything has. So wires have resistance. So if I try to push current, which is delivering the power, right? If I try to push current to a conductor, then it's going to drop the voltage. The line crew, Alabama Power, calls it line loss. That's just trying to get that current through those conductors, right? So I'm trying to get 100 watts. So 20 amps means I have to use a big wire, right? Understand that? 1 amp means I could use a little old tiny wire. So basically, the higher the voltage is, the smaller wires you can use to run that power. Which means now Alabama Power can use, instead of using copper to get that power down here, they can go to aluminum, right? Understand? But think about it. A lot of their interest outside their state, they're over 750,000 votes. So with 750,000 votes, they could push 750,000 watts of power with 1 amp of current. But the problem is, at 750,000 amps votes, you couldn't even get close to that. They'd come out and meet you. The movie I looked at, Eagle Eye. Y'all ever seen that Eagle Eye? And they break that high voltage, high tension line, and what happens to that guy? He evaporates, right? Because it just blows into pieces. So the closer we get to earth ground, we're going to have to start lowering that voltage. And then when it gets to your house, we got to but we have two voltages in our house over here. We have what we call 240, we have 120. So 200 volts, all your high wattage devices. Your dryer, right? Your HVAC system, your electric heaters, all this stuff. Because now we can run smaller gauge wire, right? You understand that? Now I can do the 2x4s in my house, right? Instead of running a big old wire under there. The advantage of high voltage is that we can push more power, right? You understand what smaller contacts, smaller relays, smaller everything. So yeah. When people says high voltage is more efficient, no, it's not. We don't pay for we pay for watts, right? You understand that? But the higher my voltage I can deliver that wattage at, the less current it takes, but the more dangerous it becomes. Where's your 240 outlets at? Some of them don't even have outlets. Some of them are hardwired. So if you've got an electric water heater, it's going to be hardwired, right? You understand? Your 240 plugs, you can't get them. So where's the 240 plug at? If the electrician followed the code, where's it at? It's behind the stove down at the baseboard, right? So what do you have to do to get to that thing? You got to pull it out, right? You understand? So 240 plugs are not easy to get to. 120 plugs all over the place. So that's the advantage of high. So that means if I'm going to run a big old motor, I'm going to run it on high voltage, right? You understand? But I don't want that high voltage inside my control cabinet, right? You understand? So we'll use low voltage in there for what? For safety. And then we'll put these power devices, and we fill them up, by the way. So there is some high voltage. But you'll see these big motor starters, they might not even be in your control cabinet. They might be in a cabinet somewhere else by themselves. And then all our control circuit does is just engage the relay or energize that relay, right? Switch over. So yeah, I've seen contactors so big they scare you. They sound like cannons when they go in because they're so big. So big question, guys. Oops. So now y'all know why y'all have 240 and 120 in your house, right? So what's the next rule? So basically control circuits usually consist of two circuits, and they're what we call the power circuit and the control circuit, right? Control circuit's usually low voltage. Rule 5, control voltage such as switches, relays, and sensors can only be used once in a relay logic diagram. Control devices that have multiple contacts can be represented multiple times in a control logic diagram. In other words, the same control device contact cannot be used. PLCs, we don't care because they're software, right? You understand? Here you got a mechanical contact, and you can't use that mechanical contact up here and do what? Use it down here. You have to use it in a different so we've got two contacts belonging to the same relay. This one is called, this is between what numbers, what, 1 and 3. This is between what, 6 and 5. This is between 6 and 7, right? You understand that? So even though they're assigned to the same relay, they're different contacts. Now in PLCs, how many times can we use a contact? Not infinite, but that would use a lot. Yeah, I don't even know if it would get close to infinity. Moving toward it, you could say. So output devices can only be represented once in a relay logic diagram, right? Signals in relay, signals need to flow from what? L1 to L2. So we don't want to hook up a relay to cause it to go back to what? L2, back toward L1. Diagrams should be numbered and commented correctly. Unlike PLC logic diagrams, horizontal lines are numbered and not rungs. So in PLC, we number the rungs, right? You understand? And no matter how many lines they got, lines don't get another number in PLC. Line numbers are placed to the left of L1 adjacent to the line Any line that aligns with a horizontal with another line, it gets the same number. Comments can be written on the left or right. Your book says, I think, on the right, but you'll see them different places on the diagram. The location of each relay contact controlled by a coil is identified by writing the line number on the right-hand side, right? We call them cross-reference numbers. Are you okay? And I think these are the roots for PLCs. Now, what's nice about PLC is that it's a computer, and if you screw up on some of these, it's not going to let you get by with it. So Allen Bradley, what did they put on the left? They put E's on the left of L1. Then you got an error. And it puts it up there instantly, so you're going to have to go back and tell it to do what? To check it, right? You understand that? But we should not have any E's before we leave or try to download that thing, right? So that's why it says error. Error will not clear until corrected. Input instructions must be placed between L1 and L2. Same thing, right? I'm sorry. Between L1 and what? The rungs load. It should be noted that any instruction that the programming application places on L1 side is considered to be an input. So in PLC 1, all we used was contacts and switches. Here we're going to have instructions that are considered to be inputs, like compare instructions. Subroutines are considered output instructions, so they're going to go on the right. Compare instructions are compare, so we're going to be able to compare things now in this class. We're going to say, okay, if this is greater than and equal to that, that's decision making. Those are going to go to the left. So we do have some instructions that, so if they pop on the left, then they're going to be considered what? Input instructions. If they pop in on the right, they're going to be considered what? Output instructions. If you put an output instruction between the input instruction, then you're going to get an error that won't what? That won't clear, right? That makes sense? Rule 2. So here we're not talking about contacts. We're talking about input instructions. Input instructions go on the left between L1 and the load, right? Output instruction goes on the right between L2 and the control device. In PLCs, there's no such things as overloads. So we will not have overloads in a PLC. If we do hook up a motor starter, the overloads will be out there on the output, right? You understand that? And we'll show you how that would work too. Rule 2, output instructions are placed between the rungs control devices or the input instructions and L2. Nothing is allowed between the rungs output instructions and L2. Nothing, right? You understand that? Rule 3, all input and output instructions must be placed horizontally. This is what? You can't place them vertically, no matter how hard you try. There's no way to rotate them. Let's talk about it. Root 4. This will cause an error until it's what? A rung output instruction must not be placed in series with other output instructions. Multiple rung output instructions can be placed in parallel, right? In another what? Line. One output instruction per line, one or more output instructions per rung. Everybody okay? You okay there, right? We just create a down drop and stick them in there. So we can have a lot of output instructions in a rung. We just can't put them in series, right? If you put one in series, what's going to happen? Yeah, you're not going to be able to download the program or anything until you create that, clear that error out. Rule number 6, relative RS logic, all rung numbers are automatically placed on the left side of each rung's first line. So that's automatic. By the way, Siemens don't call them rungs, they call them networks, but you understand that. What Siemens does is they place the network number above the rung. And each rung is in a separate network, so each rung is a separate network. So, Rule 7, user defined. This is not automatic, so this is up to you. Each input or output device instruction logical address is entered above the instruction symbol, right? You understand that? So if you don't enter an address, if you don't enter a logical address, so we're using what we call logical addresses, right? You don't understand the difference between a logical and a physical address. What's the difference? Not in computers. Computers, a physical address is the binary address that device out. And how many addresses you have will depend on the size of your address bus inside your computer. Most of us can't deal with address. We can't deal with lots. So physical address. A physical address, it's smooth and it's going to go off after. A physical address would be like a phone number. So I'm assigned a physical address, which is what? Is a phone number. But what do you do instead of using physical addresses? How many of y'all know all the people's phone numbers that's in your phone? You put a logical address in there, right? Which is a name. So logical addresses are, so you can't change. Now, technically, the phone number in this is can be changed, but you can't change it, right? So that phone number is built into this thing, right? But you can change the contact, right? So you assign logical addresses for your phone. So instead of me knowing the binary address of that output port, I come up with a logical address. I assign them. Now you have to assign it according to the syntax that your application supports, right? So how do we assign output addresses for RSLogix 500? How do we tell the PLC that it's an output address? It's an output. Start with a no, right? And then we assign a logical address to that device. We tell it the logical address for the device. We say O, right? And what we put? Colon, right? Then we put a what? We put a slot number, unless it's slot 0. If it's slot 0 is understood, right? You don't have to put that. Then we put a what? So this is the slot number. Then we put a what? Put a slash, and then we put a bit number. If we do have an output module that's got multiple words, we'd start with O, and then we would assign it a what? A slot number. Then we'd put a dot, and then we'd assign a word number, and then we'd put a slash, and then we would put a bit. Right? You understand that? Now, we're not going to have to deal with that because none of our PLCs deal with multiple words. But we can buy input modules for these modular PLCs that's got a 32. We can buy a 32-bit module, but it would still be in the same slot, right? So it might be output 2, so that would be slot 2, right? And then we'd say this would be the what? Second word, and then this would be bit 4. Now we're going to have to do this in our timers because our timers use words. They don't use bits, they use words. And so, of course, they use logical addresses on that. So our timer, we have this thing right here that stands for the what? Accumulator. And it's a 16-bit register, so I'd have to say T4, right? You understand that? Then I'd say 0, that would be the timer number. Then I'd put a dot, and then I'd put ACC because the ACC is a whole what? It's a whole word, right? You understand that? It's not a bit, it's a word. So that's where we would have to use the dots. On our timers, your preset register is a 16 is a word. Your accumulator is a word. And the source could be a word. It depends on where you get it from. Okay, does that make sense? How do we identify inputs? We start off with a what? I, followed by the what? Slot, then maybe followed by what? Word slash followed by what? Bit. If we don't have multiple words, then we can eliminate the word, right? You understand that? Yes or no? So all ours, we're going to be using 1100 PLCs. This guy has 10 inputs and he's got 6 outputs. So we don't have multiple words, so we don't use a word here, right? And since this is a hybrid PLC, what I call a hybrid PLC, you're not going to find that, but Rich calls it that. Because what can we do with this guy? So this guy has certain fixed ports. It's got 10 fixed ports, 0 through 9 inputs. It's got 6 outputs, 0 through 5, right? And it don't occupy a slot. So we're going to say slot 0, right? And we'll address a bit, but we'll find out later on that we could address. I can pull all 5 of these. I can pull all 10 of these inputs in at one time by specifying a word, right? You understand that? So we'll look at that, and then strip off the bits that we're not interested in. Are we okay? You okay, Mr. Lyle? We can specify. I can come up here and if I've got an instruction, I could come up here and I could say N. So I can say N 0.0, and I would pull in all 10 of them with one whack, one instruction, and pull them in and do things with it. We'll find out the power of that in this class, where we could pull in that whole word, right? You understand? Of course, what we'd end up with is we go through bit 9, so being a bit, it's 10, 11, 12, 13, and 14, 15 would be garbage. We'd have to strip those out somewhere, and we'll learn how we can strip off the bits that we're not interested in. So we'd get rid of those, and then we could use that. So I could load that directly into a counter if I wanted to, which is pretty neat. So I'll show y'all that. It's really neat. So I could take a bunch of switches and put in a number and load that into a counter instead of getting it from we still have to use a move instruction, but we could move it from an input port where directly into a counter, or we could move it from there directly into a timer. So that way you could actually set the time if you wanted to. So we can output multiple bits too. So I could clear out a whole output port. I could clear out that whole output port by saying output, and then I could say, I could say move, and then I could say 0, and then I could put it into output 0.0, and that would clear out my output port with one instruction. We could do that. And we'll show y'all the way they do it in Siemens. One of the things that they do on the manufacturing line over there is when you reset it, it wants to clear out all the output ports because that's the default. So the output ports when you reset it, they have it set up. So if you turn all your output ports off, it automatically goes to a certain situation. Well, they do it with one instruction. They just store zeros into that output, and what does it do? Everything goes back to where it's supposed to be. So we'll look at this as we move along. So understanding that dot indicates a what? It indicates a word. Now we're dealing with what? 16 bits. So, or whatever we have out there. We can do this on Logic Pro because Logic Pro is using 16-bit ports. So it's using word ports. So we'll show you that. But these are logical addresses. Why? Because you're the one that does what? Yeah, you're the ones that you don't make it up. You have to use the ones that are. You have to use the ones that are assigned logically inside the PLC. But you can use them where? You can use them as many times you want to. But you don't have to know the binary address of the actual device, right? And I think I showed y'all that. So your the video in this computer's got a binary address, but I don't have to know that address, right? You understand? So I can send things to the display without having to know the actual binary address. But if you want, I think I showed y'all this last semester, didn't I? This is called system information. And here's I/O right here. And so these are the addresses for the I/O. Now they're giving it to us in hexadecimal. They're not giving it to us in binary. So, but these are the actual addresses right here. That's assigned. So the speaker is that address what? 61, which would be 0110, right? 0001. That's the binary address of the speaker. So anytime you hear the internal speakers on your computer working, this is it, right? A real-time clock. This is where the real-time clock is. So anytime you set the time on your computer, this is the address of the real-time clock right there. But you don't have to know that, right? You can just bring up a little icon on the bottom. You can double-click on it, and you can set the time. You don't have to know the physical address of the real-time clock because you're dealing with logical addresses, right? Here we use a ton of icons, right? So I can actually use an icon to represent a physical address. So this is basically what we're doing. In there, we're using those. Interrupt controller, direct memory access controller, real-time clock. Here's my keyboard, my ThinkPad keyboard tab. It's that address right there, right? So so these are actually the physical addresses inside the computer. No, the fan is not. It's either on or off. They control it separately. But it would be something. If you've got a fan that runs in different speeds, it'll probably fall into one of these motherboard reset motherboard, because that'd be specific to that. If you got a fan that runs at the same speed all the time, then your laptop does. It actually controls the speed of the fan because why? Because it's trying to run on batteries, right? A lot of your desktop computers, they just run the fan wide open all the time. So so a lot of these motherboard resources would be specific to this motherboard. All these other ones, these are going to be the same. If I'm dealing with a computer that runs Windows, a Windows operating system, all these computers, these guys are going to be the same. Because that operating system has got to make the computer operate, right? So all these fixed resources that every computer has, these guys are going to be in fixed addresses. If it's not, then odds are you're going to have to load a driver which adds the address into the resources. They won't be listed here. So these are permanent resources. Memory. So memory, all your memory's got addresses. So this is the memory in the machine. Now these are big addresses, right? This guy here runs a big address bus. We got a lot of memory, but this is actually the way the memory is set up. So the memory for your audio controller would be at this address right here. A lot of memory. 65,500. No, I don't know. Audio 3FF. I would have to look that up. Notice these numbers are the same. So this is actually how much memory you have in the audio circuit for this. But luckily, I don't have to know that. Why? Yeah, logical addresses. I click on an icon here. I click on an icon there, right? You understand? If I want to print, the printer port is at an address. I don't have to know that. I just tell my operating system I want to print. I click the print, and the operating system automatically takes care of all the addresses for you. So that's addresses. I don't have to worry about the binary addresses inside this PLC. I say input 0.0, and it takes care of everything for me, right? You understand? Okay. These are user defined. We can't change change them, but we can use them over and over and over again. We decide where we need to use them, right? User defined. A comment should be added to each instruction symbol. And of course, what we're getting used to in here is making sure we use symbols, right? That's in Siemens calls them tags. So once we assign a device, and most of y'all caught on to that, right? Once you assign it a symbol, if you use it multiple times, you don't have to put the address anymore. Now you can type in the symbol, and it'll automatically insert the address for you. Here, unfortunately, here in RS Logic 500, symbols are optional. On your newer PLCs, like 5000, symbols, tags are what? They're required. So Siemens, if you don't put a name in there, it'll assign one for you. Yeah. Not automatic. Each instruction symbol should be given a name that relates to the what? Instructions function. Now what we do is we use the names that the lab gives, which makes it real easy to trace the labs through, right? So you know, every class, when we're writing these programs, they'll say the red light, and then in parentheses they'll give me that's one we use. And it's real easy to trace that. So those are the rules, guys. Y'all got any questions on those? So these are the ones we're going to follow. Of course, we need to be able to wire this up. We've got an input box, and we got an output box that we can hook up to the 1100s, and that's why we tried to go to this. And what we're going to let y'all do is we're going to let each one of y'all have a chance to actually wire up true push buttons and actually motors and stuff out here to actually run off your PLC. So, yeah. But we only have one set. We got the stuff to build them, but we just never have enough time to build them. Yeah. But we're just going to use a lab that everybody's going to be able to try it at least one time, right? So let y'all do that. So we have an input box and an output. So y'all been drawing it all the time, right? You understand? And that's one of the things that we want y'all to do. You'll still draw the way it's supposed to be connected, but then I would like you to have that because the power supplies and everything are built in here. So this thing will fold up on me. So that's one thing we like about this module, this mount. This is not the PLC, by the way. And a lot of people answered how many inputs and outputs does your PLC have, and I saw 16 inputs and 16 outputs because they were looking at this down here, right? You understand? This is not the PLC. This is the PLC. But this guy here can support this little board, and we can buy multiple ones of these. So that's what these other two slots are. So we can literally buy several. But this module right here supports 16 inputs, and it supports 16 outputs. So I can use the switches, or I can come up here and hook actual physical devices into this, which would actually go up here to the inputs up here. This guy here's got 10 inputs and got 6. Not this down here. I'm not going to tell you how many times I saw 16. Yeah, because this is not the PLC. This is what? This is the mount that the PLC's on. Well, it's actually the mount, and also, and you can Festo. This is put out by Festo, and you can buy different things to go in here. So you can buy less the inputs than this. And this, by the way, I cover up the light because it's extremely bright. But this is your minus, and then the red up here is your plus. So there's your power supply. So if I'm going to hook up, these are syncing inputs. So that means my input devices are going to have to be what? Sourcing. Right? So I'll run a wire out here, and I would run it to what? I'll run it to all my input devices. Right? You understand that? And then I would bring the other side into the input. These are sourcing output. This is a sourcing output, so that means my devices that I hook up to here would have to use negative, right? Y'all understand what I'm saying? Okay. So that's available, and we got boxes. We got switches on it. We got one that's got motors on it. We got one that's got lights on it. Yeah, takes these guys right here. This is just we call these banana plugs. They're standard size, and we could use these wires right here, but we got plenty of them. Y'all saw my one last term, the boxes. So we get the opportunity to wire up one of your truckers, you know, just for the heck of it. I mean, you take PLC3, you're actually going to do the whole thing. We get these, we'll unmount these 1100s off here, and then you'll mount the 1200s on there, and you'll do the whole wiring yourself on PLC3. And you program it. Is that right, Joe? Okay, so any questions on that? So we reviewed our ladders, right? A lot of the stuff that we're going to do is going to be automatic, right? It's going to be automatic, or if you do it wrong, it's going to do what? It's going to add. Okay, so I got my PLC here. And what's the first thing we need to do when we sort it? Number one. New PLC. It's on. First of all, we have to establish communication with the PLC. So Allen Bradley uses something called RS Links. It's inside the Allen Bradley folder on your computer. RS Links. And then we'll run RS Links Classic. And this is where we're going to establish communication with the PLC. Now, we have different ways we can connect to this. This uses the data highway. It uses the data highway or RS 485, and then we have Ethernet. So we have to establish communication, whichever one we use. So what we'll do is I'm going to go to communication, and then I'm going to go to configure drivers. And so when you come up here by default, there's not going to be any drivers on here when you first install the PLC. So right here it says available drivers. So here, these are all the available drivers that's capable, that's compatible with RS Logic 500. I'm not going to use the Ethernet. I'll check out that later. But here's Ethernet IP. So we'd have to assign an IP to the thing. So I'm going to use the we're not using device net. We're going to use this guy. Oh, I didn't list that. That's not it. Okay. And then we'll come up here and add it. And we'll see if this is the wrong one. It don't look like it. Huh? Right, but that's called, so what we're going to notice on here, and this is also true on 5000, is all these little applications are separate. In TIA, they call it the Total Integrated Automation, which means what? Everything's in one application. So it automatically will bring up and establish your IP and everything with that, but you do it here. To do the IP, what we have to do is we have to do what? We have to bring in up RS Links, pick the right driver. So here, if I was going to hook it up with Ethernet, I would choose the Ethernet driver. If I did that, then when we looked at this last semester, we would have to come up with an IP, right? Well, with the TIA portal, all that's in there. It'll come up right off the bat. It'll come up and bring up the application. When you say I want to connect to the PLC, it'll automatically launch the application, and it'll go out there and say search for devices. It'll go out there and search for the devices for the MAC address, and then you'll do what? Then you'll assign it an IP. Here we have to do everything. But, yes. Uh, it depends on how it's set up. Normally, we hook these computers up using what we call it a peer-to-peer, or ad hoc is what they call it. It means we hook directly between the device. We don't go through network switches or anything. When you do that, then it's your responsibility to assign the device. Right. Well, I mean, you can assign all the same IP as long as you don't network them together. When you network together, then you'll have to assign each one of them an IP. So a different IP, right? Which is a logical address, right? I'm trying to figure out which one is the DFI driver. I know it's not DeviceNet. I wish I'd have looked at that first. AP, so it's not the Ethernet driver, so we'll delete that. It's not slave. This is it. So what this does is this comes up and it's going to assign it to COM1. I think it needs to be COM3, I think. And this gives us the bit speed. So guys, this guy's going to scream. It's connected at 19,200 bits per second. In parity, we're not going to talk about that. What we need to do is we can go out and we can find free COM ports or stuff like that, but I didn't need to do that. What I'm going to do is just tell it to auto configure. Are y'all familiar with Device Manager? Yes or no? Or we can look and see how they're configured. Well, it depends. What we're doing is we're using so Device Manager shows us on Windows. It shows us all the devices that are being controlled by the operating system. Okay. Now, what we're doing is that our computers don't support these COM ports anymore. These are serial ports. But they do support USB. And what does the S stand for in USB? Serial. So what we do is we have a dongle that we put in here that takes USB and converts it over to the old RS-232. This is what we call a plug-and-play device, which means your operating system automatically assigns the resources to the device when you plug it in. So what we have to do is figure out which COM port it assigns to this thing. We'll unplug it and see which COM port disappeared, right? And we'll put it back in and see which COM port it came in there. So it assigned it to what? 3. So we'll select port 3 and we'll set auto configure. Let's get out of this and cancel. Let's go to add. We'll to auto configure. Okay, there we go. And it did what? So it configured it all automatically. 19,200 baud, which is faster than the 1100s. I mean, these guys right here, they transfer information at 1,200 bits per second. The 1000 transfers information at 9,600 bits per second. This guy does what? 19,200. So this guy's, I mean, when you upload them, it's going to be real fast. So I've established communication with the thing, right? Okay. So what's the next thing we need to do? So now we're going to look up RS logic. And then what do we need to do next? Need to configure the CPU, right? So we'll check comms to make sure the guy's there. We know it is.